Yeah, I mean, the introductions, you can read 1 and 2, but yeah, 3 and 6 is what that quiz was about, chapter 3.
Okay.
And what we're talking about today was chapter 6.
So this was like last week, right?
Yes, the quiz was last week. So.
Okay. And is that how you did it?
Yes.
Yes.
I'm not really worried about it. I just have a little bit of fun.
Right. Because oh, sorry, what's your name again? Monish? Yeah. Okay, cool. I did it, yeah. The current nouns, X and Y, is aligning each other. And then you just make a line for each children. But they're stored in the, oh, true, because you have a set.
Yeah, like I have to know, like, I mean, just these circles, right, kind of doesn't come any information about who they belong to, except obviously the students that belong to that one.
Yeah. Yeah, I just created a bunch of variables, like, or class variables, where it's like some set, what I'm multiplying level by.
好的，这个写了啦。你等我们看它会不会消失。加了。现在几了？现在lecture几了？好像加到80。现在说好像是对。真是。还是shooting mode。哦，就 auto 就行，还是 auto。那个估计也不能阻止他修炼。
Yeah.
下午开始看一下。开心，生活过程。
包都没带。
哎，
怎么了？
So I will give you a quick introduction to the product one you will be start doing today. Okay. So I will post the links to this in Canvas later on. But the idea is you will be implementing something called SimpleDB. And it basically has different components that we will be covering in our lecture, right? For example, today we will be talking about disk space manager, buffer manager, and the file system, right, inside a database management system. So then you have those corresponding modules in this system called SimpleDB. And SimpleDB is implementing Java. So what this documentation provides to you is the interface to all the Java classes in this system. You are not going to implement all of these methods, of course, but you will be implementing a substantial subset of this. So for example, if you look at, we just talked about aggregate, right? So there will be a class called aggregate, representing all the aggregation operator inside the SimpleDB system. Okay. Give you another example. There's a buffer pool class that actually you will be implementing part of this in your lab 1, right? Lab 1 is about storage manager, buffer manager, and heap file system inside SimpleDB. You will be implementing some of these methods in the buffer pool class. So what this documentation gives you is the explanation of different methods inside SimpleDB. What parameters it expects, what it's supposed to do, and what it's supposed to return. Does that make sense? So it's a very comprehensive set of documentation, but it will be extremely important for your implementation down the road. Okay? And that being said, let me show you the lab 1. So SimpleDB lab 1 is about using, it basically shows you how to build the system, how to run some simple tests. We're using unit test for all the labs. Basically, what unit test does is it's a predefined set of tests that packaged in this particular interface called Java unit test. Okay? So your code will be later on subject to all the unit test cases we have developed. And we actually, in the distribution of your assignment, we hand out those unit tests to you as well. So once you finish your implementation, you can simply test against those unit test cases. If you pass all of them, that means with high probability your implementation is 100% right. But it doesn't necessarily mean it's 100% right? Because there are always some corner cases, maybe the unit test cases do not cover, and your code has a bug for it. But nevertheless, for the grading of all your labs, all your project assignments, as long as you are able to pass all the unit tests we have, then you should be able to qualify for 100% of the credit. Does that make sense? Any question on that? And we are also using Ant. Ant is a package to manage unit tests, to run all your unit test cases. If you don't know Ant, that's fine. The documentation provides detailed explanation how to run Ant and how to use Ant to run your test. I will have script provided to you as well. You simply run the scripts according to the instruction given out in your lab assignment. So there's some explanation to the end. So there's something called system test. In addition to those unit test cases. So system test is a set of end-to-end test cases. Unit test cases are designed to test some individual method, right? You have implemented. Once you pass all the unit test cases, then you will run your code against what we call system test. What system test does is to run a set of test cases against your system by treating it as an end-to-end system. Does that make sense? So that the entire workflow is tested, logic, right? So for different lab assignments, we have a variety number of different test cases, number of different test cases, system test cases that your code will be subject to be running against. Okay. And then there are some more details on how to run SimpleDB. SimpleDB, once you finish compiling your code, it will produce a simpledb.jar file. And then you simply use Java to run the code. It will bring up a MySQL or pSQL like command line interface. That makes sense? Initially, of course, this command line interface cannot do much because you haven't implemented the query evaluation, optimization, those modules yet. So it doesn't really do much. But as the project progresses to lab 2, lab 3, by the end of lab 3, your code should be able to mimic the behavior of a MySQL or pSQL command line interface like environment, in the sense that you can start typing MySQL statement, SQL statements against the SimpleDB tables you have in your database, in your SimpleDB database. That make sense? You're not able to do that as yet by the end of your lab 1 and lab 2 because you haven't implemented the query evaluation modules yet. But by the end of lab 3, you will be able to do that. Okay? Once you type this command. You can also do everything in Eclipse. Of course, one way of doing this is to use just the Georgia server, right? The command line. Use Vim or Emacs to do your code editing. Or if you prefer, you can use an IDE, right? Any IDE will work. Here I give out instruction for how to do this in Eclipse, but you don't necessarily have to use Eclipse. But of course, it's impossible for me to provide instruction for each different IDEs. So I just provide instruction for Eclipse as an example. Any question on this? Okay. You can also, the last thing I want to talk a little bit is, as I mentioned before, the unit test cases and system test cases are bundled together. When you use Ant to run your code against either unit test cases or system test cases, your code will be run against all the test cases we have. But sometimes you may figure out, okay, my code didn't pass this particular test case. Instead of every time run your code through the entire test cases, you want to just run your code against that simple test case for debugging purposes, right? So this section tells you how you do that, how you change the configuration so that when you run your code, it is checked against a specific test case of your choice, either a unit test case or a system test case. Okay. Any question on this? And then here are the implementation things for lab 1, right? So basically, what you will be doing is to follow this instruction closely, step by step. So what lab 1 asks you to do is to implement the catalog, which is to store the schema information on that. We will be talking about that today, actually. Not in the context of SimpleDB, but in the context of a generic relational database system. But then you will be required to implement those concepts in the context of SimpleDB. Okay? So you will be implementing the schema support, the catalog, the buffer pool, heap file access method, essentially the storage manager, and some simple basic operators. And you will be asked, at the end of the day, your code should be run on a simple query, not through the SQL interface, because you haven't implemented the query parser, query evaluator modules yet. But at least you will be able to run your code against the hard-coded operator inside the kernel. So that's what you will be able to do at the end of lab 1. Okay? So that's pretty much about your lab 1. It is actually not a whole lot of things you have to code for lab 1, but because this is the first time you are working on a comprehensive, extensive code base. Simple DB code base is pretty extensive, as you can tell from this documentation here. For you, if you start late. If you start late, okay? If you start right away, meaning if you start looking at all the documentation I provide to you, all the examples, all the hints I gave you right after the lecture today, which I will post the details on Canvas. I haven't done that yet, but I will post that later today. You start paying attention to those and work together with your partner. Lab 1 is not that hard. The most difficult ones, in my opinion, are maybe lab 3 or lab 4. But lab 1 is actually quite straightforward. But however, that being said, it is a very extensive code base. If you haven't done any system coding before, if most of the code you've written before is a standalone program of some sort, right? Given a well-defined input, and you expect to code some algorithm, produce some output. If that's all the type of code you have written before, this can be overwhelming, right? Because there are no clearly defined a set of input and a set of output and a single program you are asked to write. Rather, it's a very extensive system code you have to implement. There are many different places you have to figure out to write your code. For example, when I was an intern at Microsoft, when I worked on Microsoft SQL Server code back in 2005, right before they released SQL Server 2005, it took me an entire week. You know, they gave me the entire code base of SQL Server, and it took me an entire week to figure out how to print just hello world when I run the SQL Server. You know, when I power up SQL Server and just to print out hello world somewhere, so that I can interact with the system a little bit. It took me a week to figure out where to do that one line of code properly so that I can actually interact with the system through that line of code. You know, inserting one line of code is easy, right? But inserting one line of code in the right place is hard. Does that make sense? That's where system coding can be challenging. Way more challenging than writing a standalone application, a single program with well-defined input and well-defined output. You know, that's where the difference is. Okay, that's essentially what you will be going through in your lab 1. Right? You may find the logic of your code fairly simple, but the really tricky part is where to put that logic to. Once you figure out where to write that logic, writing down the logic itself is actually not that hard. Does that make sense? Okay. All right. So that being said, let me come back to the lecture here today. Any questions before I proceed? Any questions before I proceed? So I will give you about maybe at most 2 weeks. I'm still debating about this. Maybe 1.5 weeks. At most 2 weeks for lab 1. Okay. Most likely I will give you 1.5 weeks for your lab 1 to implement lab 1. Then once you know, it will be like this for the remaining part of your semester. Basically, once you turn in lab 1, lab 2 will be immediately released. And when lab 2 is due, lab 3 will be immediately released, so on and so forth, until the end of the semester. There will be no gap between any 2 labs. There will be no gap between any 2 labs. And you will be, like I mentioned, you will submit your lab, all the lab assignment code through either, let's use Bitbucket, for example. Using Bitbucket private repository. You just set up a Bitbucket private repository and add TA's Bitbucket account to your repository. Basically give them access. Then at the time of due date, simply stop committing to that particular branch. So you have lab 1, lab 2, so on and so forth, right? So simply stop committing any updates to that particular branch. Once the due date is passed, then the TAs will check out your branch and run your code. So you don't have to make any submission whatsoever, right? Just commit your code to your private repository by the time of due date. Because Bitbucket or GitHub for that purpose document the timestamp of each commit. The TAs will be able to verify that your latest commit it was done before the due date. So make sure you don't commit anything to a branch corresponding to a particular lab that has already passed the due date. Because if you do that, it will be considered as a late submission. Okay, how many of you have used GitHub or Bitbucket before? Okay, so most of you, if not all of you. For those of you who haven't used Bitbucket or GitHub, very easy to learn this. I will give out a pointer to GitHub and Bitbucket on Canvas that you can go over yourself. But it's fairly straightforward. And in my opinion, it's almost a must-have skill nowadays if you're a computer science student. If you don't know GitHub or don't know how to use Git, chances are you won't be able to find a good job after you graduate. Right? So this is a good opportunity to pick up this skill anyway. Okay. Any question on the submission of your lab assignment? Okay. Oh, okay. All right. So let's continue with the discussion today. Essentially, what we will be discussing today is what you're going to implement in your lab 1. Storage manager, buffer manager, and file system. Okay. So last time we stopped right here. We talked about the storage hierarchy. We said we have cache inside CPU, we have memory, then we have secondary storage. That's your disk, either hard drive disk or solid state drive disk. I will be talking about the difference of the two later on. So the main memory, the cache is really fast, but it's the most costly form of storage media inside a computer, and it's managed by the processor itself. And there are two types of cache inside a processor. There's data cache, there is instruction cache. So since our focus will be mostly on main memory data management inside a database system, I'm not going to go into details of cache level data management. I do, however, want to comment on the fact that given that the size of main memory is growing so quickly nowadays, oftentimes you can cache, if not the entire table, a large chunk of your data inside your main memory. In those cases, the bottleneck in accessing your data in terms of speed is actually the data transfer between main memory to data cache. Okay, that becomes a bottleneck. And when you transfer data from main memory to cache, they do so using something called cache line. A cache line. A cache line is a predefined number, which is to specify how many bytes you actually transfer every time whenever you want to move data from memory to cache. For example, 64 kilobytes. In other words, even if you try to access a single byte somewhere from your memory, you have to transfer a cache line size of data from memory to the cache. Of course, containing that byte of interest. With that said, there are a lot of optimization you can do, right? Basically, to maximize what we call the locality of your access patterns. In other words, never ever just access a single byte. Rather, try to co-locate what you try to access in a cache line size, roughly in a cache line size of amount of data, and transfer all of those at once from memory to cache. Okay, so that's one form of optimization you can do over there. So that being said, let's look at memory. So memory is pretty fast as well. Typically, it's in the order of tens or hundreds of nanoseconds in terms of accessing data from memory. Generally, it is big enough, but not big enough to store the entire database. It is big enough to do caching of a large chunk of data, but not necessarily big enough to store the entirety of your database. Of course, this really depends on what kind of application you are talking about, right? If you're talking about University of Utah student database, I'm sure today's memory size is big enough to cache all that entire database. I don't know how universal user database is, but probably in the order of tens of gigabytes. That's easily that can easily fit into the memory size of today's computer. A server machine can easily have hundreds or 200s of gigabytes of RAM. Okay. However, if you're talking about Google database, right, whatever, for example, Google has a database to store the data they crawl from the web, that's in the order of petabytes, right? That's at least in the order of petabytes. Obviously, you cannot hope to cache the entirety of that database in your main memory. So you have to, in those cases, rely on secondary storage media, like hard drive or SSD drive, to store those additional data that cannot fit in your main memory. Okay? So one thing I want to comment on regarding memory is, so memory is often known as RAM. Okay? Does anyone know what this word stands for? What does RAM stand for? Random access memory. Right? Does anyone know why this is called random access memory? Why people call memory random access memory? Why you don't call this, for example, sequential access memory or whatever access memory? Why is it called random access memory?
You can access the memory from any part of the memory.
Yeah, excellent. So point number one, you can do random access. Meaning, no matter what's the last position you have accessed in your memory, you can jump to another arbitrary position inside anywhere in your memory space. If you virtualize your memory space like this, the point is, no matter where you were from your last access, you can always jump to a new location without any constraint. That's point number one. Okay? Point number one. You may wonder, okay, isn't this always the case, right? Given any storage media, I can always do random access. That's not true, right? That's not true. In some cases, you cannot do random access. You have to, in order to access a particular location, you have to go through the entire memory space sequentially in order to reach your location. One way to think about that is, think about the boarding the plane, the process of boarding the plane. Nowadays, boarding the plane is kind of like fighting a war, right? And people always try to bring, because they charge so much on your check-in luggage, so everyone try to put a lot of carry-on luggage, right? Not a problem for me, because I fly so much, I'm always the first one to board the plane. Because when you accumulate so many miles, you become a whatever membership with the airline, they ask you to board the plane first. But if you observe how people board the airplane, is that there's a long queue, right? There's a single corridor walking down the plane, right? So if you are that person, so if this is a plane, right? These are seats. This is the corridor. And you see there's a stream of people coming down. If you are here, and your seat is here, you have to wait. You have to follow the stream going down these aisles until it reaches your row and you sit down. Right? That is not random access. That's sequential access. In order to reach your destination, you are sequentially accessing all the rows until it's your turn. Does that make sense? And what's the downside of that? It's slow. Right? You know how boarding the plane how slow can it be, right? So this is sequential access. Random access is kind of like you have the entire plane to yourself. You have the entire plane yourself. You can run up and down inside the plane. And until you go row 14, you go. And then until you go row 42, you can go immediately without any blocking or anything like that. So that's the difference between random access and sequential access. Make sense? Okay? Okay, once you understand that, let me explain the second point, why people call this random access memory. Another point, a bigger point actually, that oftentimes people do not pay attention to or do not realize, why people call memory random access memory, is that it takes you constant time to access anywhere from your memory space. In other words, no matter where you are at the moment, and no matter where you're going to access next, suppose currently you are here, and you try to access something somewhere, some number of bytes from here versus you're trying to access some number of bytes here. Option 1 and option 2 will take roughly the same amount of time for you to do. In other words, it doesn't really matter where you try to go in your memory space. It always takes constant time. It's a constant cost. It's a constant cost. It's a little bit counterintuitive, right? If you look at this picture here, you may argue, if you go back to the airplane example I just gave you, if you're in row 14, I tell you to go to row 15 versus I tell you to go to row 42. Intuitively, it should be cheaper, taking less amount of time for you to go from here to here versus going from here to here. But that's because you are a human being. You are a physical, mechanical object. It takes time for you to work down the aisle. Where in this case, memory, as I said, there is complex physics going behind this, but from a really high level point of view, you are using electrons to store all those bytes or bits, 0 or 1, right? So accessing memory is done through the electron traveling through this memory space. And electron, as I mentioned, electrons travels at almost the speed of light. So when you travel at that particular speed, the difference in the distance, amount of distance you traveled, is negligible. When you can travel at that speed, what's the light of speed? Anyone can tell me that?
3 to 10 to the power 6
Yeah.
kilometers per second.
Okay, 3 to the 10 to the power 6 kilometers per second. If you are travel at that speed, and you look at the time for me to travel from here to the door over there, or take me to travel from here to downtown Salt Lake City, make no difference. Literally, there's no difference. Okay, that's why it's viewed as a constant access cost, no matter where you go. Okay, so that's another point regarding random access memory. That's why people call this random access memory. First of all, you can do random access. Secondly, you can do random access at constant cost. Okay, that's why people call memory random access memory for that reason. Next, we'll talk about disk. As I mentioned in the earlier example, when your data is so big that you cannot fit your entire database in memory, you have to store data on a secondary storage media, such as disk. And there are two types of disk primarily in today's computer. One is hard drive disk, also known as magnetic disk. The other type being solid state drive or flash drive. So what's the difference of the two? So magnetic disk use magnetic field to store 0 or 1 bit. We all know magnetic field has two polarized directions, right? North and south, right? So using those, I can differentiate 0 or 1 bit, essentially. That's the basic principle behind it. And the other nice thing about this is, if you have a magnetic field, it actually persists through or without any power supply. So even if you lose power, you cut off power supply to your computer, those magnetic fields will persist, through a long time. And eventually, of course, if your time is eternity, eventually magnetic field will die down as well. But for the lifetime of a hard drive disk, the magnetic field is considered to be persistent. And that means a really nice property of disk is non-volatile. Compared to memory, memory is volatile, meaning if you lose power or cut off power supply to your computer, everything stored in your memory will be lost forever. Okay? So that's a key difference between storing data on disk versus storing data in memory. Of course, the downside of storing data on disk is that it's much slower to access data from disk versus accessing data from memory. And furthermore, the other thing I want to comment on, and I will illustrate in details in the next few slides, is that hard drive, whether it's magnetic disk or solid state drive disk, they both support random access as well. They both support random access. But we don't call them random access disk for the reason that if you do random access on disk, it actually matters where you go. The cost of doing random access on a hard drive disk matters, the location where you try to access data matters a lot. That determines the cost of your random access. I will explain this later on. Okay? That's another very distinct feature of accessing data from disk. So I mentioned solid state drive. There are also tapes which I will skip because this is really for archiving purposes. If you have large amount of data, so large that goes beyond what your disk is capable to store of, and you rarely access those data. For example, data from back in the 1970s onwards. We rarely access those data, but occasionally I need to check against some record over there, but rarely I'm going to access those data. In those cases, most likely I will push off those data to tape. Tape only supports sequential access. It doesn't really support random access, meaning if you want to access a particular location, you have to start from the beginning and do a sequential scan until you reach that position. For that reason, it's very slow. But it has the highest capacity. That's why it's used for archiving purposes. Okay? So here is the big picture. You have cache on the top, you have memory, and there's a line over there, meaning that whatever above that line is volatile. Whatever below that line is non-volatile. You have SSD, hard drive, and tapes. And if you go this direction, bottom up, you got higher and higher speed of access. If you go the other direction, from top to bottom, you got you got lower price in terms of dollar per byte. How much you have to pay to store a single byte? How much you have to pay to store a single byte? If you go from top to bottom, this value goes down. Dollar per byte goes down. Okay. So this memory hierarchy introduced data transfer between different storage media, meaning transferring data from hard drive to main memory, transferring data from SSD to main memory, and transferring data from memory to cache. You may wonder why you need to do all this data transfer. The reason is processor, your CPU, can only access and operate data from the data cache inside the CPU. So in order for CPU to do anything, you have to bring data to the data cache. But in order to get data into data cache, you have to first get data to memory, because cache only interfaces with memory. So you have to have your data in memory. Then a tiny subset of it will go into data cache for processing, and then after that's done, return back to memory. And because your data is potentially even larger than the memory capacity, you have to store some additional data on disk, either hard drive or SSD drive. And because of that, you have to do data transfer between this hard drive disks and SSD drives to memory. So this introduced this sequence of data transfer that's actually critical to the performance of your system, because data transfer can be slow. It can actually become a bottleneck of your system. So that's why you want to do everything you can to optimize data transfer in different storage medias. Okay? So that's what we'll just talk about. And now some formalization of what I said. Okay? So people, given this observation, and people try to come up with abstract models to describe moving data between different storage medias and doing data access at different levels. The most popular model, one of the most popular models is called RAM model, random access model, where this V shape represents your CPU, represents a processor of any kind, right? Then this yellow box represents your RAM, your memory space. And the model here basically says I have, from a theoretical point of view, I can consider myself as infinite amount of memory, I can do uniform random access cost. Those two things I mentioned. And in this computation model, I never have to worry about moving data from disk to memory because I have infinite amount of memory. So everything fits in my memory, no matter how large the data is. Of course, that's an unrealistic assumption. So this is really just a theoretical model people use to analyze computer programs. So most of the algorithms or data structures you have learned so far implicitly assume this particular model. Right? For example, you guys have learned sorting before, right? Quick sort, bubble sort. And the instructor who taught sorting method to you probably didn't mention the RAND model at all, but he or she was using the RAND model when he or she was talking about that particular algorithm. The reason is you always made the assumption that your data actually fit in memory for you to do the sorting. Have you ever thought about what if my data doesn't fit in my memory and how do I do sorting in that case? How do you do sorting in that case?
Bringing half chunk, half chunk.
You can bring half chunk,
And like partial chunks of memory into that.
Yeah, but the thing is, how do you compare one chunk to another chunk? Because the comparison, in order to do that comparison, you have to somehow access data from memory and access data on disk at the same time. But that's almost impossible, right? You can only access data from memory. So when you bring the next chunk in, you have to kick out the existing chunk in memory. So it's not that trivial. Okay? So we will be talking about how to do that later on. So far, for the most of stuff you guys have learned from algorithm and data structures, in fact, you are implicitly assuming this. You have infinite amount of memory, or alternatively, what you're saying is, I have small amount of data. Right? I have small amount of data you can fit in memory. Right? What if that's not the case? Well, if that's not the case, this becomes your picture. Right? You have level 1, level 2 cache, you have RAM, then you have hard drive. For the purpose of this class, for the most part of this class, maybe towards the end of the semester, if I have time, I will talk about data transfer between RAM and cache. But for the most part of this course, we're going to ignore that effect, the data transfer between memory and cache. So basically, we're going to ignore these two layers, level 1 and level 2 cache. We will focus on just the data transfer between RAM and disk, meaning the RAM model, the classic RAM model no longer holds. When your data is so big, so that they cannot fit entirely in your memory, then that classic RAM model fails. When that model fails, we introduce this model called external memory model. External memory model. External memory model. And talking about external memory model, in order to understand this, we first need to understand how that secondary storage media works, how the hard drive works. And there are two types of hard drives. One is magnetic field hard drive, the other is solid state drive. I will be talking about both. Let's start with magnetic field drive. Magnetic field drive. The most common type of secondary storage media. This is what an abstraction looks like for a magnetic field hard drive. Okay, that's probably running on some of your computers. What it does is there is what we call a magnetic surface. Magnetic surface that's stored north of source depending on the magnetic field you have, and that represents 0 or 1 bit. And there is an arm, this red color beam. That's what we call a disk arm. This disk arm is able to convert magnetic field into electrons, into positively charged or negatively charged electrons, meaning turning data from your disk to something the memory can understand. Okay, so that's the physics over there. And then what happened is I organize this magnetic surface into what we call track. A track is nothing else but a circle with same radius to the center of this surface. So this is a track. So basically, it's all the small surface units that form a circle with same radius to the center of your surface. That's what we call a track. And a magnetic surface has multiple such tracks, obviously, multiple such tracks. And the way you read data from hard drive is to move this arm in and out to align the head of the arm against a particular track that holds your data, and then wait for the surface to rotate. For example, the data you're trying to read is from this particular part. Just aligning the head of the arm to that particular track is not good enough. You got to wait for that portion of data from that track rotated right under the head of your arm. Does that make sense? So there are two actions involved. One is moving the head of the arm to the particular track that has your data, and wait for the surface to rotate that segment of data you're trying to read from the track to be right below the head of your arm. And once the data you're trying to read is rotated under, just below the head of your arm, you can start converting data from magnetic field to electrons, meaning transfer data from disk to your main memory. So that's essentially the way it works. So that's kind of the model we're talking about, right? So this line here between memory and hard drive is that process I have just described. So given this discussion, there is, if you look at the access time versus amount of data you are trying to access, there is this phenomenon that initially is roughly kind of like a linear curve. Why that? Because it takes you constant time to read 1 unit of data. 1 unit being, let's say, 8 bytes or whatever unit of your choice, right? 8 bytes, 16 bytes, or even 8 kilobytes, whatever. You come up with a unit. Then it's constant time to access that unit of data from your main memory. So with the amount of data you're trying to read, trying to access is increasing, the total amount of time, cumulative amount of time to access those amount of data is a linear curve, roughly a linear curve. Right? The angle of the curve is the rate, the speed of accessing that unit of data. Right? However, until a certain point, you see a sudden jump in the cost of accessing those data. When that happens, that's when the amount of data you're trying to access now has exceeded the capacity of your memory. Then no longer is a linear curve. Because you have to do the moving of the arm and wait for the rotation. That's way slower than doing random access in your memory. Okay? So those are the concerns I have highlighted. You want to do this efficiently, however, doing data transfer from disk to memory is slow, for that reason we have just talked about. So how do we improve this? Well, there are a couple of things you can do. One is improve raw data transfer speed, meaning from a hardware manufacturing point of view, I can somehow produce faster disks. I will talk about where that coming to picture later on. There's a really important parameter you should watch out when you buy a new hard drive next time. But from a software point of view, we can also do the following to improve this data transfer. One is to avoid untimely data transfer. The other is to avoid unnecessary data transfer. Both of this, I will just mention them for now. I will come back and explain them in details later on. What do I mean by untimely and unnecessary data transfer? So basically, you are at this layer, right? This is database manager. Then the buffer manager inside your database management system is the one who is responsible for achieving these two objectives, right? Avoid untimely data transfer and avoid unnecessary data transfer. Because the buffer manager interface with your database manager is in charge of all the data transfer between memory and disk. Okay, that being said, let's take a closer look at and try to come up with an abstraction model to describe what's going on. So from an abstract point of view, there are really two operations you need to worry about. One is read, one is write. Read basically means you're trying to read data from disk to memory. And write basically is the reverse of that. You're trying to take some data out of your memory and write it back to the disk. So those are the two abstraction you need to have. But why not store everything in memory? That's obviously not possible. First of all, it costs too much, and second, the memory capacity is limited, right? You can of course buy more memory, but you have to pay more. And how much more you can buy, right? Your data eventually will still be exceeding the capacity of the memory you have. So you gotta store this on disk, but the problem with storing this on disk is a notable challenge is random access versus sequential access. I will highlight this in the next few slides. What do I mean by the difference between random access and sequential access when you read data from disk? To understand that, first of all, we need to understand whenever you read or write data from or write data to a disk, you never do so in a single byte. You never do so in a single byte. You do this in a unit of bytes. That unit typically is either 4 kilobytes or 8 kilobytes. That's what we call a block or a page. These two mean the same thing in this class. A block or a page. This represents nothing but a collection of bytes that you access at the same time. That's the smallest unit of data you operate over. The smallest unit of data you're going to operate over. And the typical size for this is either 4 kilobytes or 8 kilobytes in modern database systems. So that means that a disk really looks like this. You have multiple of these surfaces I mentioned earlier. In fact, that's what we call a platter. In modern hard drive disks, a platter typically is double surfaced. The platter is typically double surfaced, meaning you have surface on top, you also have surface at the bottom. This is the arm assembly, the holding all the arms. 2 arms per platter because you have the upper and lower surfaces. The head of the arm, this black region, is capable of converting magnetic field to electrons, doing the actual data transfer from disk to memory. Then there are channels connecting this all the way back to main memory. That's what we call memory bus. Okay, I'm not going into the details of that yet.
But the 2 arms on each of the platter, they move together or independently?
Yes, they move together.
Okay.
They don't move independently of each other. Okay, and then you have multiple such arms, the 2 per platter, and you have multiple platters. That together form your hard drive disk. And how do you store data on this hard drive? Basically, you have, this is what we call the track I mentioned earlier. Right? This is what we call the track. And this small white region, that's what we call a sector. That's the smallest unit that the hard drive can support to access to. Typically the size of that is 512 bytes. Meaning, if you know the device driver for a particular hard drive, right? That's what we call block device driver. And you can write code at that level. That's a fairly low level code you can access to. If you have access to that low level of drivers code, the smallest unit of data, even you can access that low level of driver code, the smallest unit you can operate over is still bounded by this thing called sector. And typical size of that is 512 bytes. Database systems, of course, can choose to access data using just this concept of sector, meaning every time I read or write a sector of data. You can do that. However, as for the reason we will be explaining later on, a typical page inside the database is basically much larger than 512 bytes. That's because the record size is fairly large. If you operate on just 512 bytes, there are just a few records you can accommodate. But typically, you don't write or read just a few records. You want to read and write a bunch of records, maybe tens or hundreds of records together. When you do that, accessing a single sector at a time is a waste of your travel time to the disk. Rather, you want to bring a few sectors together every time when you pay a visit to the disk. So that's the idea. For that reason, a block or page is a few neighboring sectors. A few neighboring sectors. The typical, what do I mean by a few? Oh, well, that's the value of this is different for different systems, but typically this is, like, for example, 8 or 16. Right? So 8 sector, that means 4 kilobytes. 16, that means 8 kilobytes. The size of page or block. Okay? So once you understand all this, now let's try to understand what's going on here, right? So I have a sector, all the sector with the same radius to the center of this hard drive is what we call a track. And all the tracks from different surfaces with the same radius to the center conceptually form what we call a cylinder, And how you read data from this is, suppose you are trying to read that particular sector over there. What you do is you move the arm in and out so that the head of arm is aligned with that particular track. Then you wait for the disk to spin, to rotate, so that that sector is rotated right under the head of your arm, that track wheel. Then you can start transferring data. While you are transferring data, remember this is still rotating, right? This is still rotating. So while data is being transferred, this is rotating, so you are transferring data continuously over this sector or a few sectors of your choice, of your interest. Okay, so that's how it works. Okay, there's an abstraction of that, which I'm going to skip. So these are some typical parameters for hard drive. So if you understand what I said so far, we can characterize the way you access data using these 3 particular costs, using these 3 different components. Right? One is what we call seek time. Seek time refers to the time it takes you to move your arm to position the disk head on a particular track. Of course, the seek time, if you think about this, seek time is a variable, right? Seek time is a variable. Why is that? If this head is here and you're trying to access this particular track, your seek time is 0, right? You don't have to move your arm at all. But what if you're trying to read some data from this track? Then you have to move this guy out, away from the center of the spindle, right? That takes time. And the time it takes for you to do that obviously will be different from versus like moving from here to here versus moving here to here. So that's a variable, right? It's not a constant. Nevertheless, it's a fairly small surface, right, in terms of the radius. So the time it takes for you to move the handle arm from one location to another, the difference is fairly small. For that reason, these manufacturers do not actually, most these manufacturers do not give you that difference. They will just give you a single value to represent the average seek time for their hard drive disks. They will just give you a single value for that parameter. Okay, so that's seek time. The other thing is called rotation delay. What does rotation delay mean? Well, once you have paid the seek time delay, you now at this point you know the head of the arm is aligned with the track you want to read data from. Nevertheless, you still have to wait for the data to be rotated under the head of your arm. So suppose the head of your arm is here, but the data you're trying to read is still here. So you have to wait for this guy to rotate to become this. This takes time. How long this takes? Well, it takes the hard drive to rotate this amount of distance. How do you calculate this? Well, you need to know how fast this guy is rotating at. And that's an important parameter all of you should pay attention to, called rotation per minute. Right? If you go to, for example, and you look at 1 by Harvard. This is a very important parameter they always highlight. And that's the parameter you want to pay attention to. Why this is important, coming back here, that's because your basically that value determines your rotation delay, RPM, rotation per minute. So for example, 7,200 RPM. What does that mean? That means you are doing 7,200 rotations per minute. So how long it takes for you to do one rotation? How do you do that calculation? Somebody tell me.
Get the circumference and
You use this. Right? Why that? Because you are doing 1 minute 60 seconds, right? You are dividing time by this many rotations. That's how long it takes you to do one rotation. Does that make sense? Once you understand that, you can calculate this time, right? What you do is use this distance divided by the distance from an entire circle. This gives you the amount of time to do this rotation. Make sense? Okay. So that's the rotation delay. That's the rotation delay. Of course, calculating this, you are not able to calculate this, right? Because how do you know where this is when the head arm is just aligned with this particular track? So what typically happens is you use the average case analysis. The average case analysis is, this is the general case, right? Average case, this is the best case. And what's the worst case? The worst case is, worst case happens when, so at the time when you align the head arm to this particular track, it just right past you, just rotate right past you. So you wait a whole rotation for it to come back. That's the worst case. The best case is this, worst case is this. What's the average case? Average case is half rotation. Right? Average case is half rotation. And people use that as the rotation delay. Okay? So once you know the RPM, you know the rotation delay. Half rotation. The time to do half rotation. The last component in this whole process is what we call the transfer time, which is the time. Okay, transfer time is, so you had it aligned to this, right? But it takes time to go from here to here. This is not necessarily just a sector. Let's say this is a page. So it's a few sectors. It's a few sectors. It takes time for you to scan through this region that holds the data you want to read. And that's what we call the transfer time. And transfer time has actually two subcomponents. One is very clear, is you have to wait for this to rotate over. So it takes some rotation time. And secondly, while it's rotating, you have to do that conversion from magnetic field to electrons. So transfer time consists of both. The rotation time for the amount of data you need to read. How do you calculate that? Well, you look at how many sectors you are reading versus how many sectors you have from one track. The ratio of the two tells you how much you are rotating, actually, percentage-wise, compared to one entire rotation. Then you use that percentage of time times the time to do one rotation, that gives you the time to rotate this much of data. The second component, which is the conversion time, in most cases we ignore that conversion cost. The reason is the conversion happens pretty fast compared to that physical rotation delay. So in other words, this is dominated by the time to do the rotation itself. So in most cases, we simply view transfer time as the time to do the rotation itself. Rotation for the amount of data you try to read. Okay?
So again, it's a function of RPM.
It's a function of RPM and function of RPM and also the number of sectors you try to read versus the total number of sectors from one track. In most cases, if you're reading a small set of data, small amount of data, these three, if you look at these three values, the total cost is dominated by sync time and rotation delay. You can safely ignore the transfer time. However, if you're reading a large amount of data, you cannot ignore the transfer time. For example, you're reading this plus all the other track. Right? You're reading like few gigabytes of data. You cannot ignore this transfer time. In those cases, sync time and rotation delay, the initial sync time and rotation delay become eligible, negligible compared to you can safely ignore those costs because they will be dominated by the transfer time itself. Okay, so that's pretty much what I want to say here. Okay, the final remark I want to make regarding hard drive is the concept of next. So you arrange page or blocks sequentially on a hard drive. So what do I mean by next block or next page? Well, next block or next page always refer to the next page or next block from the same track. And when you have exhausted all the pages or blocks in the same track, you go to the next page from the next track of the same cylinder. What do I mean by that? Well, for example, you have exhausted all the pages from this track. You go to the next track of the same cylinder. Then you go to the next track of the same cylinder. Why you arrange pages or blocks like this? The reason is, when you are doing this, when you go from one track to another track, you don't have to pay any sync time delay. You may have to pay a rotation delay, because when you're moving from one track to another track and you're trying to read the next page, chances are the next page might have just rotated, bypassed the head of the arm. But that's fine, you only pay the rotation delay, you never have to pay sync time delay. What if you have exhausted everything from one cylinder? Well, next page becomes the first page of the first track from the next cylinder. The next cylinder being the cylinder with a slightly larger radius to the center of your spindle. Okay, so that's the concept next. Okay. Now I want to show you some experiments we did. Okay. Once you understand what's going on here, let's highlight the difference between sequential access and random access. In this case, I'm doing an experiment using a sequential workload, meaning I'm reading block after block following this concept of next I just mentioned. So I read the first page, then I read the next page, I read the next page, I read the next page, I read the next page. So it's sequential access. Okay, imagine I pay a sync time delay, I pay a rotation delay, I read the first page, then I continuously read page after page, and I only read the next page at a time. Okay, so that constitutes a sequential workload. So how do you understand this picture? Here, x-axis is the time, in cumulative sense. Okay, y-axis represents the location of the block you're reading from in terms of offset. Let's say offset is calculated with respect to some base address on your hard drive. So this is 0, this is 1, this is 2. So basically it's a value indicating how far off you are to that base block. So it's an offset value, essentially. As you can tell, given that the offset value is a linear curve, linear line going up, obviously I'm doing a sequential access. Okay? Then I'm reading sequential offset values. I'm reading from those locations. So far so good. And this is my sequential workload. Now I'm adding another workload, what I call RR workload, random rate workload. So I'm doing two workloads at the same time in parallel. So this space manager has a scheduler. They will serve these two requests in an interleaving fashion. So we'll serve the sequential access a little bit, come back, serve that random read workload a little bit. As you can tell, that sequential workload is still visible, right? And this little dot, this obviously represents a random workload because you are reading from random offset locations, no particular pattern whatsoever. You follow me? Okay? Now I'm adding 2 random workloads at this point. Now you can no longer tell that sequential workload anymore. The reason being that you are serving these 3 workloads in an interleaving fashion. Even though that sequential workload is indeed doing a sequential access, but because you are doing interleaving of services of 2 random workloads, by the time you come back to service that sequential workload, it's no longer sequential anymore. The head of arm is moved to a random location. It has to come back. So that sequential workload is completely destroyed for that reason. Does that make sense? You can no longer tell that sequential workload anymore. You may wonder, so what? Well, the impact is the bandwidth. How fast you can read data from disk. The blue line on top is that sequential workload running by itself. You get about 70 megabytes per second out of this disk. The theoretical upper bound of this hard drive we're using is about 80 megabytes per second. That's what the manufacturer tells us. If you look at the hard drive specification, so sequential workload almost can saturate the bandwidth of your hard drive. 70 megabytes versus 80 megabytes per second. There is a 10 megabytes gap, for various reasons. There is overhead in memory bus and so on and so forth, right? Follow me? Now, if you look at the total bandwidth from that sequential and single random workload combined, meaning I'm not measuring just the sequential workload, I'm measuring the combined bandwidth from that sequential and random workload together, well, you notice that it's much lower than that 70 megabytes per second already, even though you're doing 2 workloads at the same time. But because it's a sequential mixed with random, because you're moving arms back and forth, you already suffer a drop. And when you add 2 or 3 random workloads, completely destroyed. Your bandwidth becomes just 10 megabytes per second. Combined bandwidth becomes just 10 megabytes per second, even though you're still doing that sequential workload. What this tells you, let me ask this question though. If I do the same experiments using RAM, using random access memory, what do you expect? What the curve will look like? It will be constant, right? No matter how many random workloads you mix with that sequential workload, the combined bandwidth will be the same to that single sequential workload, that blue line on top. But since you're doing this on disk, the back and forth moving of your arm, the rotation delay destroy everything. And this actually gave you an idea to launch an attack to, for example, any cloud service providers. Why you can do this attack? Well, if you go to Amazon Cloud or other cloud or Google Cloud, what they're doing is they're using virtualization, right? Each client is given some virtual machines. So you don't have a dedicated physical resource allocated to you. So you have some virtual machines, and several virtual machines share the same underlying physical resource, meaning the same physical disk. So you may observe, okay, this person is doing a sequential workload on his or her virtual machine and enjoy really high speed. Suppose that's your competitor. That's Microsoft. I'm Google, right? Both of us are using Amazon Cloud. I don't want you to be so fast because the faster you go, the better your user experience will be. So what I will do, I will rent a virtual machine on the same physical box as your virtual machine. And my virtual machine will do nothing but just do some random workload. I do nothing, I just do some random workload. Of course, yes, there's a cost for me, I have to pay for that virtual machine, but the cost I pay for that brings a significant drop in performance for Microsoft virtual machine. And that costs Microsoft money. And that cost for Microsoft, if you look at this, if you measure the cost in terms of the bandwidth you can serve your customer, 7 times drop. Right? 7 times drop. By simply renting a virtual machine and running random workload. Just do whatever you want to do in random fashion, access data from disk. Does that make sense? So that's kind of one attack you can do already. Right? you know your friends are doing some stuff on virtual machine, try to rent a virtual machine next to his or her on the same physical box, then do this. So, okay, so that's so much about the disk-based manager part. Okay, now you understand what's going on over there. Next, let's look at buffer manager. So one thing I haven't talked about is solid state drive. In the interest of time, I decided to move on to the buffer manager part, and I will come back to the solid state drive next lecture. Okay, come back to the solid state drive next lecture. Now, buffer manager, if you understand what I said so far, you will understand why we need this thing called buffer manager, right? Why we need this particular module called buffer manager. Okay, your data is much bigger than your memory capacity, so you have to store some additional data on disk. And because of that, you have to do data transfer from disk to hard drive. From disk to your main memory. And that data transfer can be costly, as we see from that simple experiment I demonstrated to you, especially if you're doing random access. So what you want to do is you want to minimize the number of times you pay your visit to your disk. The ideal situation is whenever you want to access some data, that data magically is already available in main memory. So you never have to visit the disk at all. So in order to do that, database systems introduce something called buffer manager, which is highlighted in this picture here, which is nothing else but a reserved space in your main memory, a reserved space for your main memory, organized by pages. So each white rectangular box here represents a single page or block, So in this case, I have simply a collection of pages or a collection of blocks sitting in my main memory, reserved, in this reserved space. A white area, a white box represents a free page, a free block that's to be used. A black box represents a page or block that's occupied by some page or block you previously read from disk, and you cache them in your buffer, in your memory buffer. Now the way it works is, if somebody requests this particular page, the way this works is as follows. So if I have, this is my hard drive, and this is my buffer, under this line, I'm doing data transfer. The way it works is some higher level process from your CPU, using my notation, it's like B-lash. So this is CPU. And this will send a request asking for a particular page. And a buffer manager will expose an interface called pin page, where you supply a page ID. So for example, I will pin page number 10. What that means is some request, some process is asking for page number 10, asking for the data in page number 10. And initially this is all empty, right? There's nothing here. So page number 10 is sitting somewhere here. And you basically do the rotation, you do the seek time and rotation. So if I zoom in to this, that's the picture I got. Then wait until this is here. Boom, you got your data, you transfer that to memory. Okay, so far so good. Once you have that page in memory, what you do is you place that page into your buffer. At this point, you can place that page anywhere in your memory. It doesn't really matter because it's random. Whether you place here or here, it takes the same amount of time for CPU to access that data. So let's say I place here. So now this is page 10. Now you return this request with, there's a frame, this is what we call, each of this is called a frame, and this 1, 2, 3, 4, 5, 6, I return frame number 6. I return the frame number to the CPU so that the CPU knows, oh, page 10 now is in frame number 6. That's it. Now next time if somebody, okay, I can pin page, for example, 11, which is maybe here, so I will bring this here, so on and so forth, right? And sometime later, somebody will ask for page 10 again. Now at this point, you don't have to go back to this and fetch that page anymore. It's here, boom. You get it, return right away. You avoid that expensive random access to disk. By the way, I forgot to mention, the time to do random access on disk is typically at least 10 times more expensive to do random access for the same amount of data in the memory. So you save your access cost by roughly tenfold. But eventually something will happen, right? Every frame is occupied. And somebody asks for pin page 20. Let's say 20 is not in any of your frames. And 20 is sitting somewhere here. Page 20 is sitting somewhere here. And none of this holds the page you're asking for. What you do, while you have to pay a visit to the disk and bring this back to memory, now it's here, and you try to place this into buffer, now you have a problem. You run out of space. Right? It's kind of like everybody wants to get into business class on a flight. Guess what? Not enough space. What do you do? In that scenario, what do? You pay, right? You pay money, right? So of course, one choice is, okay, you have to pay. But you cannot attach dollars to each page on disk, right? You cannot do that, right? So you cannot pay. You cannot simply ask them to pay. So you have to figure out some other strategy to figure out who get into business class, right? For example, maybe you can call Delta or American or United today and say, okay, I have a brilliant idea. Instead of asking customer to pay, use some other feature to determine who can get into business class. For example, how many times you fly with me, and I don't know whether you have taken a database class before or not. Things like that, right? So what are the features we're using here to determine who get into the buffer, right? Who is replaced? That's what I'm going to discuss next, but I think I've run out of time. So I will stop right here. I didn't cover everything you need to know about Lab 1. Nevertheless, you should start reading the documentation on Lab 1, which I will post the detail on Canvas later today. One more thing is, today at 2, I have a meeting, DGS, Director of Graduate Study at the grad school. For that reason, I have to move my office hour from 2 to 3 today to another time slot. I will make an announcement in Canvas on that.